have to leave early, they could just look at the video. Sweet. All right, so if you remember, we're on the last page for chapter 7. So we're gonna finish up chapter 7 today, and then we're gonna go on to chapter 8. So let me go ahead and switch over to my notes on, oh, let's go over to my notes. Yeah, let's try this again. All right, so let's actually start out with the TI-84. So let's go to stats and let's go edit. So for your TI-84, you should have, hopefully you have entered all the data set here. So that's the first thing you want to go ahead and do. Enter the data set into L1. So I'm going to clear up L2. And we're also going to clear up L3 just to make sure everything nice and clean, so on and so forth. All right. So the first thing what we want to go ahead and do, if you look at the notes, so the first thing is that in your calculator, construct a histogram of the data. And then it said describe the distribution. So we're going to go ahead and do that. So once you enter the data set into L1, what you want to do, you want to go into graph. All right, so if you look at mine is already highlighted or is already zoomed into the histogram, but I'm pretty sure for most of you, if you hit graph, you're essentially gonna see a blank screen. So if you wanna actually look at your histogram, what you wanna do, you wanna go to the zoom option. And since we're zooming in on the stats, you wanna hit number 9 where it says zoom stats. All right, so now we get the histogram. So let me kind of sketch out how does the histogram look on my notes. So the histogram looks something like that. All right. So if you look at the data set, if you look at the histogram, what type of shape does the histogram have? Is it skewed to the left, skewed to the right, or can I say this is normally distributed? All right, so right, so I'm guessing skew right. Well, the one that you're seeing right now on my screen. Yeah, so you should hit zoom and hit zoom 9 or zoom stats. All right. So if you look at my graph right here, it kind of looked like it's skewed to the right. All right, so let's pay attention on how to go to the histogram. So for a histogram, what you want to do, you want to hit second. You want to go to y equal to, and you want to go to plot on. So on, you want to make sure it is on. If you go down, then what you want to go ahead and do is move to the right, and you want to select the histogram. So to select the histogram, you press enter. For the X list, just make sure you tell it it's L1. And then you just go to graph, and then make sure you hit zoom 9. All right, so everybody should have this histogram right now. For that issue, you might have to talk to me during my office hour because, like, I know probably what's wrong with it, but I really can't help you out right now because it's kind of like a lengthy process of like checking a bunch of stuff. All right, try that. All right, so we have this histogram which is skewed to the right. So now what I want to do, I want to check my probability plot that we learned yesterday. So we want to look at the probability plot and see based off of the probability plot, if you remember, if we get a straight line, that means we could say that our data set is normally distributed. If we get something that has curvature, that's kind of telling us that our data set is not normally distributed. So we're going to go back to second, y equal to, we're going to go back to plot on. And this time, instead of selecting the histogram, we're going to select the very last one. So we're going to select this one, which is the probability plot. So we're going to select this. And now if you look at it, it says data list. It says data list, we're going to say L1. And for the data axis, you're going to say it's the x-axis. So once you choose that the data list is L1 and the data axis is X, what you have to go ahead and do, go to graph. All right, so if you look at the picture, it's really, you can't really tell because we have to focus in on it. So to focus in on it, we're gonna press zoom and and we're gonna go to zoom stats. Right. So based off of the probability plot, does this probability plot, does it look like a straight line or is it kind of curvy? Yeah, so I'll draw here the probability. Wait, so we found out that the probability plot is kind of showing that it's kind of curvy. All right. Everybody good that the probability plot has a curve to it? All right, so let me go and hopefully I should be able to share my notes. Cool. All right, so this is what I have written so far. So based off of based off of the histogram, we kind of saw that skew to the right. Based off of our probability plot, it's kind of showing the probability plot is kind of curvy. So Parsi said, is the data approximately normal? So based off of the histogram and based off of our probability plot, can I say that our data set is normal or is this data set not normal? So we'll say no, it is not normal since the histogram is skewed right and the probability plot Great. All right, so we're saying no, it is not normal since the histogram is skewed right and the probability plot is curved. Like in order for us to say that this is normal, our histogram should have given us something that kind of looks symmetrical. Also, our probability plot should have given us a probability plot that pretty much resembles a straight line. So since this one has some curvature to it, that's why I know our data set is not normal. And that's it for chapter 7. All right. Everybody good on this? Wait. All right. So before we go to chapter A, Let's do some sort of activity. All right. So in this chapter, we're essentially going to transition over from having a sample size of 1. And what we're going to do, we're going to transfer over that we have a sample size bigger than 1. So when we say that we have a sample size bigger than 1, what it's saying that instead of me saying find the probability that an individual, say, have an IQ score greater than 100, what we want to find out, instead of you finding that an individual have an IQ score greater than 100, what we want to do now, we want to find what's the probability that a group of people have an IQ score higher than 100. So what that's going to look like, oops, sorry about that. It could look something like this. And we're going to transition over to this. So this is what we learned for chapter 7. And this is what we're going to learn in chapter 8. So instead of me finding the probability that one individual have an IQ score greater than 100, what I now want to find out, I want to find out what's the probability that a group of n many people have an IQ score of 100. So say if I wanted to find out like a group of 5 people, we will say that what's the probability of this group of 5 people that the average IQ score is greater than 100. So that's what we're going to be doing for the sampling distribution. We're not going to be sampling one person at a time. What we're going to be doing, we're going to be sampling n many people at a time. So to kind of demonstrate that, what we're going to do, we're going to do this. So what we're going to randomly do, we're going to randomly choose a number from 0 all the way through 9. Can't do math right now. So what we're going to do, we're going to randomly choose a number from 0 through 9. So what we're going to do, well, not what we're going to, well, what you're going to do, well, I'll do it too. We're going to randomly select a number from 0 through 9. So we're not actually going to randomly select it ourselves. What we're going to do, we're going to let the calculator randomly select this number for us. So what I want you to do on your calculator, and I'll show you what to do in your calculator. What we're going to do, we're going to randomly select a number from 0 to 9. So to randomly select a number from 0 to 9, what I want you to do, I want you to hit the math button. So go to math. I want you to go over here where it says PRB. So in case you are lost, you go to the math button and you go over where it says PRB. So under PRB, what I want you to do, I want you to go to number 5 where it says ran int. So for the ran int, what we're going to do, we're going to tell it what's the lowest number you could possibly choose, and we're going to tell it what the highest number it could possibly choose. So for this one, if you want it to be from 0 to 9, what should be the lowest number that we wanted to choose? All right, good job. So we're going to put 0. What should be the highest number that we wanted to choose? Wait. All right. What happens in mine? Yeah. So math, PRB, we do ran int. So we say 0, comma, 9. All right. So what I want you to do, once you do this, I want you to enter the number that you got. So you type it below this. So, and I'll get my number. All right, so I got the number 9. Coded data. All right, so far we got 3, we got 5, we got 3, we got 5, we got 4, we got 9, we got 6. Alejandro. We got 3, we got 2, we got 9, we got 2, we got 3, and we got 9. Yeah, so let's see how many numbers I got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5. All right, so we got more numbers. We got 2, 2, so. All right. Anybody else got numbers? All right. So let me show you what I have. All right, so those are my data sets. So I got 3, 5, 3, 5, 4, 9, 6, 3, 2, 9, 2, 3, 9, 2, 2, 7. So if you kind of look at all the number, they're kind of like jumbled all over the place. Oh, I think you got a new number, 0. So if you kind of look at our numbers, they're kind of like jumbled all over the place. So I want to see how does this look like in a histogram. So let's go over here in the histogram, or let's go to our calculator and let's draw a histogram, since we should know how to do a histogram. So we're gonna go to stats, we're gonna go to edit. So I'm gonna clear out this 72 data set and I'm gonna put my new data set. So I'm gonna put 3, 5, 3, 5, 4, 9, 6, 3, 2, 9, 2, 3, 9, 2, 2, 7, and 0. All right, so that's my data set. Everybody get how to enter the data set? So what we want to do, we want to see how did this distribution look when we randomly selected only one number. So we're going to say second y equal to, we go plot on, and we'll go right here where it says histogram, because we want to do a histogram. We tell it is an L1 is our X value. So let's go ahead and graph this. So we graph it. So if you look at it, it's not looking at the right place. In order to make it to tell it to look at the right place, we go to zoom, we hit 9. All right. So if you look at this histogram, how does the histogram look? Does it look normal? Wait, all right, so it doesn't look normal, good. So that's all good news. All right, so that's a sample size of 1. So it kind of showing us that our distribution is not normal, because if it would have been normal, most of the data set would have been in the middle. But if you kind of look at our data set, it kind of like scatter all over the place, except for, well, I can't really highlight it. Well, I can if I do that. Like it kind of scatter all over the place, except for here, like right here, you have a high concentration in this bin. But if you look at most of the bin, it's kind of scattered all over the place. All right. So that's it for that. So I'm going to show you what I wrote down so far in my notes. So if you look at this, we're gonna say not normal. Like, does it make sense that this is not normal, or like, is it kind of confusing? Why is it not normal? Well, if you look at all of the number, are all of the number equally likely to occur, or is there one particular number that more likely to occur if we have number from 0 to 9? Well, if you look at the number, since we have a random number generator, these should all have the same chances of occurring. So if all of them have the same chances of occurring, if you kind of remember back to chapter 6, when we did the uniform distribution, technically this should have a uniform distribution, because since we have number from 0 to 9, all of the number are equally likely to occur. So it should have a uniform distribution. So it kind of makes sense that it's not normal, because if we're randomly selecting one data set, like if we're only randomly selecting one data set, like it shouldn't be normal. It should still be not normal. But what we're gonna do now, we're gonna increase our sample size. So what we're gonna do, we're gonna increase our sample size to 5. So what we're gonna do, we're gonna randomly select 5 number, and once we get those 5 number, I want you to take the average of those 5 number. So right now, I don't want you to do anything. All I want you to do, pay attention to me, so that way you know exactly what you're supposed to do. So on your calculator, we go back to second quit. So we go back to math, we go back to PRB, and we still do random int. So we still want the lowest number to be 0. We still want the highest number to be 9. But the only thing different now, I wanted to give you back 5 number. So if I wanted to give it back 5 numbers, I want you to hit the number 5. And now instead of just giving me back 1 number, it should give me back 5 number. So if you look at my 5 numbers, it gave me back 9, 1, 5, 4, 7. So once you get those 5 numbers, this is what I want you to do with those 5 numbers. So right now you shouldn't be doing anything, just paying attention to me on what am I going to do with those 5 numbers. So once you get these 5 numbers, I want you to take the average of those 5 numbers. So hopefully you still remember how to take the average. You add up all the numbers, and then you divide it by however many numbers I have. Since I have 5 numbers, you divide it by 5. So we get 9 plus 1 plus 5 plus 4 plus 7. You get 26. And I want you to divide it by 5. If you do 26 divided by 5, you get 5.2. Everybody kind of see how I got the 5.2? All right, so now what I want you to do, I want you to do that. So I want you to find your mean. Here, don't give me the mean right now. So once you find your mean, I want you to type it below where it says type below. So Julian, if you retype it in, that'll be awesome. Perfect. Right now you're taking the average of 5 numbers. Because essentially what we're trying to do, we're trying to prove the sampling distribution. 4.4, 5.4. All right, do I have any more number? All right, 7.4. 4.8. Any other number that people haven't typed in? All right, so let us stop it here. All right, so if you look at my new number sets, so compared to what we got before, when we did only one sample, this is when we only randomly selected one number. This is if I randomly select a 5 number. So if you look at it, which one look more like, which one does all the number look like closer together? Does my first data set look like the number are closer together, or does my second data set look like the numbers are closer together? By closer together, I mean like they're not spread out that much. So which one have a smaller spread? Cool. So if you notice, the second one have a smaller spread. Because if you look at the first one, since we're just randomly choosing one person or one number in this case scenario, it's kind of easy to get like a 0 or a 9. But if you look at it, if instead of me randomly selecting one number, if me randomly selecting 5 number, it's kind of harder for me to get like 9 or 0. Because if I wanted to get an average of 9, what's the only way that I could get an average of 9? Like all my numbers have to be what? Yeah, so all my numbers have to be 9. So it's not very likely for me to get all 9 or also all 0. But if you look at it, which number kind of occurring the most often? And you forget about the decimal, just look at the like the whole number in front of it. Yeah, so if you kind of notice 5 is occurring more often because there's more combination for 5. You could kind of think about it like you could get an average of 5 if you have a 1 plus 9, or if you have 2 plus 8, or if you have 3 plus 7, or 4 plus 6, or 5 plus 5. So it's easier for you to get an average of 5 because there are more different combinations that you could get for the average. Versus for 9, there's only one particular way that you could get an average of 9, and that is if all of them are 9. So now what I'm going to go ahead and do, I'm going to go ahead and do a histogram of this data set. So if I do a histogram of this data set, do you think it's going to look more normal than this one? Or do you think it will look less normal? So less normal or more normal? So we're going to say, oops, we're going to say more normal. So I'm going to go into my TI and I'm going to enter this for my data set. So let me transfer over to my TI-84. So what we're going to go ahead and do, we're going to go ahead and go to stats, edit, and let's change this data set. So we're going to put 4.4, 5, 4.8, 4, 5.4, 5.6, 5.4, 6.8, 5, 3.4. All right, so I enter my data set in here. So we're gonna do a histogram. We're gonna see, does it look more normal? So we go second Y equal, we'll go plot on. We'll go right here. So we still want to do a histogram, so we'll leave that alone. We'll say X list is L1. Let's go over here where it says graph. And what do you notice happened with the histogram? It became more normal. So here, let me try this. So if you look at it, it became more normal. So I'm gonna draw that in my sheet of paper. So it became more normal, it became more symmetric. So let me go ahead and see if I could do this. So what I want to do right now, I'm going to plot my first histogram and my second histogram. Let's see how does it look a little bit different. Let's see if this works. All right, that really doesn't work. You can't really see the difference. Unless, let's see if I can change it. No, you can't change it. Okay. Cool. So yeah, so if you notice, it became more symmetric. So it kind of showing you like, if you increase the sample size, so instead of just me randomly selecting one number, me randomly selecting 5 number, it actually made it where our data set became more symmetrical. So let me go ahead and go back to my notes. Go into our notes. All right. So it became more normal. So the bigger the sample size, the more normal it got. What do you think will happen if I do a sample size of 30? Do you think it will become a little bit more symmetric, or do you think it will become less symmetric? Yeah, so we get a sample size of 30, and then we take the average of those 30. So it should become more normal. So this is what we're pretty much going to be doing for chapter A. Instead of us taking a sample size of 1, what we're going to do, we're going to take a sample size of n many. And that sample size of n many is going to be more symmetrical than if we take a sample size of 1. Because if you kind of remember, when we first started with a sample size, it was non-normal. But if you look at it, as we increase our sample size to 5, it became more and more normal. So that's what chapter 8 is about. Like, I'll get into like the particular about like how big of a sample size do we need to become more symmetrical and stuff like that once we get to the chapter. But this is what we're pretty much using. We're trying to go like, hey, if I take a bigger sample size, what's going to happen to my distribution? And usually they call the first distribution the parent distribution. And then whatever distribution we get from the parent distribution, they usually call it the child distribution. Oh, I'll try and spell child. Because essentially, since we're getting it from the parents, whatever we get from the parents, we're going to say that's the child. All right. Everybody kind of okay with this theory so far? All right. So Now let's go to chapter 8 notes. Well, it's not always going to be symmetric. I'll let you know when it will be symmetric because there's something called the central limit theorem, which go into like when can we say the child distribution will become normal. Oh yeah. Okay. All right. So let's get to chapter 8. So chapter 8, we're not going to be focusing on a single mean or a single x value anymore. What we're going to be doing, we're going to be focusing on the sample mean. So that's why we're going to have some new calculations. So instead of saying mu, we're going to be calculating mu of x bar because this is the mu of the new, well, of the child distribution. So mu of x will just equal to mu because essentially it's saying like whatever the mean was before, the mean should still remain the same. But if you look at my sigma of the child distribution or sigma of x bar, it's saying that that the sigma or the standard deviation is going to change. So the standard deviation, the way we're going to calculate it is by doing standard deviation divided by square root of n. So kind of think about this. This is the standard deviation of the sample size of n. But theoretically, it goes standard. Oh. So sigma, the x bar, is essentially the standard deviation of the child distribution. So the child distribution is when we take a sample size of n many. So theoretically, the name in the book is called the standard errors. So whenever you see standard error, they're telling you, they're talking about sigma x bar. Because the thing is, kind of think about it, if I get a bigger sample size, the bigger sample size should be more accurate. So since the standard deviation, like if you remember for standard deviation, the smaller it is, the more accurate it is. So in this case, if I get a bigger sample size, that means my standard of x bar or standard deviation of x bar should be going smaller and smaller and smaller. So the bigger the sample size is, the smaller the standard deviation of x bar should be getting, or your standard error. So that's why our z-score formula is this new z-score formula. So if you notice, the old z-score formula was x minus mu divided by sigma. But we have to make some adjustment because we're not doing the z-score of a singular selection. We're making the z-score for an n many selection. So instead of putting x, you put x bar. Instead of putting mu, well, you put mu of x bar. And instead of putting sigma, you put sigma of x bar because you want the standard deviation of the child distribution, not of the parent distribution. And then it just all worked out to be this over here. All right. Any question in regard to the new formula for our z-score? All right. So this is where we come to how do I know if the sample size that I took is big enough for me to say that our distribution can now be considered symmetric or normally distributed? So this is where the central limit theorem is applied. So if you look right there, it says if x, the parent distribution, is not normally distributed, we can see if the central limit theorem apply. So we only want to use the central limit theorem if I don't know the distribution is non-normal. If I already know the distribution is non-normal, then the child distribution will also be normal. So if I already know from the beginning that the parent distribution is normal, so we'll say this is the parent, then I already know that the child distribution will also be normal. So we use the central limit theorem to check to see if our distribution is non-normal. So say like the last one that we did, where it was kind of like uniform, we want to apply the central limit theorem for that one. And we want to see, based off of the central limit theorem, can I say our data set is approximately normal? So for this one, the rule of thumb to check to see if our data set could be approximately normal, all you have to do is check for this. So n has to be greater than or equal to 30. So if my sample size is 30 or bigger, I could say our data set is approximately normal. If n is less than 30, I cannot say that the data set will be normal. It has to be, n has to be greater than or equal to 30. If it is, we say it'll be approximately normal. If n is actually smaller than 30 and the parent distribution is not normal, then you say the distribution is not normal. So, and I have some drawing in a little bit that kind of should hopefully help you out with that. Right. Any questions so far in regard to the central limit theorem? All right. All right, so let's look at these parent distribution. So if I look at this parent distribution, what type of distribution is that? And all you have to do is be able to rate. Yeah, cool. Uniform. All right, what type of distribution is this one? Cool. Symmetric, or we could say it's normal. What type of distribution would I say this one is? That's skew, perfect. All right, so let's say this is A, this is B, this is C. Of the three distribution, which one should I not apply the central limit theorem? A, B, or C? And there should only be one answer. All right, so we got one for B. Let's see if we can get more votes. All right, one for C. All right, two for C. All right, two for C, one for B, and then 20 non-respondent. All right, one for A. All right, so now we got three for C. All right, so if you remember, if we go back up here, if you read right here, it said if X, the parent distribution, is not normally distributed, we can see the central limit theorem apply. So if I look at B, if B not normal, so you're telling me B is not normal. Yeah, so B is normal. So if I already know my parent distribution is normal, like wouldn't the child distribution already be normal? So for this one, we don't need CLT. Easy for CLT. CLT stands for central limit theorem. So for distribution B, we don't need the central limit theorem because since I already know our distribution is normal, anything that come out from that normal distribution, so any child distribution that we get from it, will also be considered normal. But which of my distribution are not normal? Okay, so we have C, And we have A and C, good. So for A and C, we do need the central limit theorem. And I want to write that twice. All right. So if you look at it so whenever our distribution is non-normal, you want to use the central limit theorem because you want to see based off of the central limit theorem, can I now say that our distribution is approximately normal? But if it's already normal, we don't need the central limit theorem. All right, so what the central limit theorem says, it doesn't matter the shape of your distribution. It could be uniform, it could be normal, it could be left skew. If we have a big enough sample size where n is greater than or equal to 30, then the child distribution, then the child distribution will be approximately normal because of the central limit theorem. Yeah, I think I changed it because when I first created Canvas, I used some own notes and I've been tinkering with the own notes, so they might be a little bit different. Yeah, but I'll upload these so that way you'll have these when you're looking at the correct thing. But they should have a different one. Like it's not gonna look like this, but it should have like a different drawing. Like if you look later on. So that's what the central limit theorem is saying. It doesn't matter how your parent distribution look like. If you take a big enough sample size, the child distribution will look approximately normal, which this is showing. So remember, in order for us to say a data set is approximately normal or a child distribution is approximately normal, n has to be greater than or equal to 30. All right. Everybody good with this? Or somewhat okay with it? And like we'll do some example and hopefully the example should help out. All right, let's do these examples. All right, so right here, what I want you to do is describe the sampling distribution of the sample mean. So whenever I say describe the sampling distribution of the sample mean, essentially I'm asking for three things. So the three things I'm asking for is mu of x bar, sigma of x bar, and I'm also asking you to tell me if it's not normal, normal, or approximately normal. All right. So let's find what, so if you look at the problem, it says describe the sampling distribution of a sample mean for mu is equal to 20 and sigma is equal to 12 for a sample size of 9 if the sample come from a normal distribution. All right, so let's look at mu of x bar. What is mu of x bar equal to? So mu of x bar is equal to mu. So if mu of x bar is equal to mu, mu is equal to what? All right, 20, perfect. And that's it for that one. Let's do sigma of x bar. Sigma of x bar is equal to sigma divided by square root of n. So what was sigma divided by square root of n equal to? Well, it was equal to 12 divided by square root of 9, which give me 4. All right. Everybody good so far on mu of x bar and sigma of x bar? Okay. So now we're going to make a comment about the child distribution. I'm either going to say the child distribution is non-normal. If it's non-normal, that means the problem doesn't state the distribution is normal, and it failed the central limit theorem. So when it failed the central limit theorem, it means that the sample size was too small. If it's normal, normal means that the problem states that the distribution or the parent distribution is normal. If it's approximately normal, that means that the problem doesn't state that is a normal distribution, but the central limit theorem does apply and our sample size is greater than 30 or equal to 30, and we can say it's approximately normal. So if you read the problem, does the problem said anywhere that is a normal distribution? All right, so 2 yes, 1 no. All right, cool. So the yes have it. If you look right there, it said it has a normal distribution. So we say it's normal. Because if I know the parent distribution is normal, then the child distribution must also be normal. And that's it for A. Any question in regard to A? All right, let's do B. So for B, it says describe the sampling distribution of the sample mean for mu is equal to 20, sigma is equal to 12, for a sample size of 100 if the sample come from a skewed distribution. All right, so I'm gonna go ahead and set up. So I'm gonna find mu of x bar. We're gonna find sigma of x bar. And I wanna be lazy. So I'm gonna copy this. All right, so what is my mu of x bar equal to? 20, good job. All right, what was sigma of x bar equal to? So remember, I'm not asking for the sample size, I'm asking for sigma of x bar. So sigma of x bar will equal to sigma divided by square root of 100, which square root of 100 is actually 10. So if you do 12 divided by 10, you get 1.2. All right, everybody good that sigma of x bar is equal to 1.2? All right, cool. So in this one, does the problem state anything about the distribution or the parent distribution being normal? Yeah, if you actually look at it, it says parent distribution is skewed. So they actually tell us this is skewed distribution. So they're telling us the parent distribution is skewed. So since I know the parent distribution is skewed, I know it's not going to be normal. So it's either going to be not normal or it's going to be approximately normal. If it's not normal, that means it failed the condition of the central limit theorem. If it's approximately normal, that means it passed the condition of the central limit theorem. So what's the only condition for the central limit theorem? Cool. N has to be greater than or equal to 30. So let's look at my N. So N in this case is 100. Is 100 greater than or equal to 30? Cool, yes it is. So I'm not gonna say that this is non-normal. We're gonna say this is approximately normal. And that's how you apply the central limit theorem. All you have to do in this case scenario is just see if N is greater than or equal to 30. If it is, you say it's approximately normal. If it's not, you say it's not normal. All right. And that's it for B. Any question in regard to B? All right, so let's do C. So it should say, what do you notice about sigma of x bar? So yes, that is the only condition that for this class we're going to be using. All we're checking for if n is greater than or equal to 30. All right, so what do you notice about sigma of x bar compared to A compared to B? Well, which one's smaller? B. So if you kind of notice as the sample size is increase the standard error sigma of x bar got smaller. So as the sample size is increased, the standard error sigma of x bar got smaller, which just makes sense because kind of think about it, like which sample size are you going to trust more? A sample size of 4, or sorry, a sample size of 9, or a sample size of 100? So, and if you're having a kind of hard time, like kind of think about it like in Amazon. If you go to Amazon, if you have two products, both products have like 5 stars, but one product only have 9 review and the other product have 100 review, like which one are you gonna trust more? You're gonna trust more with the product with 100 review because like, okay, yeah, it is good that 9 review came up with all 5 stars, but you might not have a big enough sample size. But if you have 100 people who reviewed it, that might be a little bit more accurate compared to the product that only have 9 review. All right, and that's it for that problem. Any question in regard to sampling distribution? All right, let's scroll on down. All right, so what I want you to do, I want you to try this one. So I want you to do exactly the same thing. Find mu of x bar, find sigma of x bar, and I want you to tell me, here, let me just copy this. You know, want to copy this. All right, so do that one for me. And if you finish it, if you want me to double check the answer, yes, put it on the chat. Or if you want, you put it in the private chat. And to kind of make it easier for you, you say this is A, this is B, and say this is C. So that way you don't have to write out like mu of x bar and stuff like that. right, so let's go ahead and do this one. Here. All right, so let's do A. So A, like if you ever get this question, that should be probably like the easiest answer. Mu of x bar is equal to mu, so you go 30. So sigma of x bar is equal to sigma divided by square root of 20. So if you do sigma divided by square root of 30, or square root of 20, sorry, you should get 1.34. So be careful with that. Cool. Lastly, we're going to do C. Yeah, good. So we're going to do C. So if you look at the problem doesn't even mention anything about the distribution. They don't tell us if it's normally distributed. They don't tell us if it's skewed to the right, skewed to the left, or like normal or uniform. They don't tell us anything about it. So since they don't tell us anything about it, we either going to say it's not normal, or we're either going to say it's approximately normal. So to check to see if it's approximately normal, you have to check the central limit theorem. So the central limit theorem said if n is greater than or equal to 30, it's approximately normal. So if you look at my n is 20. 20 is smaller than 30. So the central limit theorem does not apply here because my sample size is not big enough. Since my sample size is not big enough, you would say that the child distribution is not normal. And that's it for that problem. Okay. Any question in regard to that problem? B was 1.34. So if you do 6 divided by square root of 20, you get 1.34. All right. So let's go ahead and let's move on. Correct. A is 30. Because if you look at mu is equal to 30, and mu of x bar is equal to mu. So everybody should be good on how to describe a normal distribution. So if we're describing a sampling distribution, those are the three things I'm going to ask for. I'm going to ask for mu of x bar, sigma of x bar, and I'm also going to ask you for is the data set normal, approximately normal, or if it's not normal. So you do kind of want to get in a habit anytime it says describe the sampling distribution. Those are the three things I'm asking for. All right, so we're gonna go ahead and do this problem. So in this problem, what we're gonna wanna do, we're gonna wanna find the probability of this event occurring. So this is gonna be a very basic problem. I just want you to get comfortable on how to find the probability for this one. So if you look at this example, it says mu is equal to 70, sigma is equal to 20, n is equal to 16, and they tell me the distribution is normal. So for this problem, do I need to use the central limit theorem? Cool. So I'm going to put right here, oops, we do not need to check the central limit theorem since the parent distribution is no. Nobody can see my writing right now where it says we do not need to check the central limit theorem. Ah, that's weird. All right, let me just reconnect. Let's reconnect. All right, everybody can see the we do not need to check the central limit there. Blah 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 blah. Okay, cool. Yeah. If that ever happens, just let me know. For that way, I could disconnect and reconnect. Because on my end, it was showing that it was showing. Cool. All right, so everybody ready to how to find the probability? Well, ready or not, here we come. All right, so let's do A. So for A, it's saying find the probability that X bar is greater than 67. So let's go ahead and draw this out. So I'm going to show you two different ways on how to. So if you remember, we only check the central limit there if they tell us the distribution is not normal. So since they already told us the distribution is normal, we don't have to use the central limit theorem. We only use the central limit theorem when our data set is not normal. So if they would tell us the distribution is skewed to the left, skewed to the right, or uniform, we use the central limit theorem. But if I already know the problem is normally distributed, you essentially don't need to check the central limit theorem. Well, this is for this problem over here. La, 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 la. All right, so let's do this problem. All right, so I'm gonna show you two ways how to do it. So one way I'm gonna show you with A, the other way I'm gonna show you with B. Like any way you do it, you should still get the same answer. All right. So what number should I put right here in the middle? So remember, the number that go in the middle is always gonna be your mean. In this case, my mean should be 70. I also saw somebody put 0. You don't put 0 unless once you find the z-score. Once you find the z-score, remember, then your mean and your standard deviation is now 0 and 1. But since we haven't found the z-score, you can't really say the mean is 0 because I still haven't found it. Once you find the z-score, then you can say the mean is 0. All right. Up next, let's go ahead and find this. So we're gonna find mu of x bar. We're gonna find sigma of x bar. So what's my mu of x bar? Mu of x bar is equal to what? 70, good. What about my sigma of x bar? What was sigma of x bar equal to? Perfect. So you do 20 divided by square root of 16, and that should actually give you 5. All right, any question how I got mu of x bar is equal to 70, sigma of x bar is equal to 5? Okay, so for this problem, I'm actually gonna find the z-score. So remember, the formula for the z-score is x bar minus mu of x bar divided by sigma of x bar. So if you look at it, x bar is this number over here. It's 67. Because remember, we want to find what's the probability that the average of those 16 objects, that the average of those 16 objects is greater than 67. So that way you say x bar is equal to 67. Then we're going to do minus mu. And you're going to divide this by our standard deviation of x bar, which we found to be 5. Everybody get, I got 67 minus 70 divided by 5. Okay, so if I do 67 minus 70, what would I get? Let's check that again. I think you might have hit 5 instead of negative. So if I do 67 minus 70, what do I get? Remember, guys, I'm saying 67 minus 70. Minus 3 over 5. So if you do minus 3 over 5, you get negative 0.6. So this is my z value. Z is equal to negative 0.6. Everybody get how I got z is equal to negative 0.6? All right. So now that I found z is equal to negative 0.6, there you go. If you do z is equal to negative 0.6, what's my mean and what's my new standard deviation now? Zero and one, good. Here, let me do a different color right there because I do want you to. So now instead of putting 70, I'm gonna put 0. Because remember, once I find that z-score is telling me, okay, now that I standardize my data set, now that I standardize x bar into a z value, now the mean convert back to 0. Now my standard deviation convert back to 1. So now if I put negative 0.6 is over here, which side should I shade? Should I shade the left side of negative 0.6 or should I shade the right side of negative 0.6? Cool. And the reason I know to shade the right side, you have to look at this inequality. That inequality is telling me to shade the right side. So if you still remember what we did yesterday, pretty much this is what we did yesterday. We did normal, CDF, and what should I say my lower bound is? All right, we're forgetting something on that though. Yeah, so remember the lower bound is negative 0.6. What's my upper bound? All right, good. 10 to the 10 power, and that's it. So this will give me the probability that z is greater than negative 0.6. But it will also be the same answer for the probability that x bar is greater than 67. So let's go ahead and do this on my TI-84. So I go on, say bye-bye to that. So we go second, we go to var, we go normal CDF. So my lower bound will be negative 0.6. So negative 0.6. My upper bound will be 10 to the 10 power. And mu and sigma stay the same. So then you answer that. And you get 0.7257. You get 0.7257. And that's it for that problem. So we get the probability that of a group of 16, that the average is greater than 67 is equal to 72%. So let me switch over back to my notes. For that way you can see that. All right, so if you look right here, I put this as the answer, but you can also put this as the answer because both of them are the same. So you can either say the probability that x bar is greater than 67 is equal to 0.7257, or you could say probability that z is greater than negative 0.6 is equal to 0.7257. All right, and we're all done with A. Any question in regard to A? All right, so let's do B. So B is gonna be you rely only on the TI-84. So this is, you're gonna tell the TI-84, here's the information, and you're gonna rely that you enter the information correctly and that the TI-83 will give you the correct answer. Because the TI-83 will give you the correct answer as long as you input it correctly. So let's go ahead and do B. So for B, we're gonna go ahead and draw this out. The middle will be 70. So if you look at this problem, we want to find the probability that x bar is less than 72. So if you look at 72, should I put 72 to the left of 70 or should I put it to the right of 70? Cool. Good job. So to the right. So remember, 72 is bigger than 70, so that way you put it to the right. All right. So which side should I shade? Should I shade to the left of 72 or to the right of 72? Good, left. Everybody go with that so far? All right. So you still have to calculate this, but we already calculated on the last round, so cool. So you still want to calculate what mu of x bar is equal to? Yes, mu. And it's what sigma of x bar is equal to, which is sigma divided by square root of n. So up next, we're going to do, we're not going to convert it to a z-score. What we're going to go ahead and do, you're going to go straight into our calculator and we're going to do normal CDF. So we do normal CDF. So for this one, what's my lower bound? What's the lowest value that gets shaded in red? Oh, perfect. Negative 10 to the 10 power. What's the highest value that I shaded in red? Cool. All right. So for this one, should I yet tell her that the mean and standard deviation is 0 and 1? Perfect. So you shouldn't tell them that because you didn't find the z-score. So what you want to tell them, what the mean of the standard deviation is, but you want to tell them these mean and this standard deviation. If you tell it the standard deviation is 20, it will give you the wrong answer. So you do have to tell it the standard deviation is 5, not 20. So for this one, we'll say mean is 70, standard deviation is 5. So let's go ahead and let's do this problem. So let's do new share. Cool. All right, so we go second, bars. Oops. Oh, let me turn it on first. We go second, bars. We do normal CDF. So we go lower bound. Lower bound will be, oops, will be negative 10 to the 10 power. My upper bound will be 72. Lower bound, well, sorry, my mean will be 70. My standard deviation will be 5. You go to paste. Cool. So if you're doing this in the calculator and you have to input it, you put negative 10 to the 10 power, comma, 72, comma, 70, comma, 5, close parenthesis. And you press enter. And we're done. So we get the probability that x bar is less than 72 is equal to 0.6554. Right. Any question on how I enter it into the calculator? All right, so let me switch back to my notes. So that's it for B. So if you look at how I put the answer for B, that's how I enter the answer in for B. So you could do either way, but you do kind of want to know how to find the z-score in case I tell you find the z-score for this value. All right, so let's do C. Correct, 0 and 1 are for z-score. Why are we not finding the 7? All right, so let's do C. So for C, which way do you want to do it? The first way or the way that we just did it right now? So the way we did it for A or the way we did it for B? Very cool. So B has it. So 70 would go in the middle. So we want to find the probability that x bar is greater than 77. So if I want to find the probability that x bar is greater than 77, would 77 go to the right of 70 or would it go to the left of 70? Oh, good job. Alright. So now, should I shade the left side of 77 or should I shade the right side of 77? All right. So for this one, we're going to jump right into it. So we'll say normal CDF. So for this one, what's my lower bound? 77. What's my upper bound? Cool. Infinity. Cool. What's my mean? 70. What's my standard deviation? All right. So let me go ahead and do this. So we'll do 77, comma, 10 to the 10 power, 70, comma, 5. So if you do this in your calculator, you should get that this is equal to 0.0808. And that'll be it for that problem. Any question in regard to that last problem? All right. So what I want you to go ahead and do, I want you to go ahead and do D. So this is practice. So practice on D. Once you get the correct answer or once you get your answer, all I want you to do is just private message me, or if you want, you put it on the chat. And for that way, I can let you know if you got it correct or if you still need a little bit more work on it. All right, so for this one, hopefully you're able to get 10, negative 10 to the 10 power, all the way to 58. And then mu is 70, sigma is 5. And for this one, you should, oh, that hurt. You should get the probability that x bar is less than 58, which is 0.0082. And that's it for D. Everybody good on how to do these type of problems? All right, so this is just like a warm-up problem. So let's get to the actual problem with the word problem. All right, so for this one says, suppose the elevator had a max capacity of 16 passenger with a total weight of 2,500 pounds. Assume male weight follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. So first thing you want to go ahead and do is get all the number and just label what all of the number represent. So what does the 16 passenger represent? Cool, N. So we say N is equal to 16. Correct, example. All right, what does the 182.9 pound represent? Mean, correct. So I say mu is equal to 182.9. Lastly, what does the 40.8 represent? Cool. so we're good with that. All right, so we got N is equal to 16, U is equal to 182.9 pounds, sigma is equal to 40.8. The 2,500, pretty much we don't use that right now. All right. So for part A, it says, for this problem, do we need to apply the central limit theorem? So for this one, do I need to use it? Cool. So we'll say no, since the parent distribution is normal. All right, good job. So no, we don't need to use this since the parent distribution is normal. We only use the central limit theorem only when the sample, well, sorry, only when the parent distribution is not normal. But if we already know it's normal, pretty much the central limit theorem, we can tell it is normal. So why bother? All right, so let's do B. So for part B, it says find the probability that one randomly selected male has a weight less than 156.25 pounds. So for part B, how many males are we selecting? Cool. So that's one. So for part B, we actually have a sample size of 1. So for this one, if we have a sample size of 1, and if this problem wasn't normally distributed, I couldn't be able to find the problem because the data set is not normally distributed. But in this case, since they already told us the distribution is normal, it's okay for me to proceed and find this probability. All right, so if you look in the bottom, I already have the normal distribution. So I have to look at where 156.25 is. 156.25 is somewhere over here. So which side of that red line should I shade? Should I shade the left side or should I shade the right side? Yeah, because if you look at it, it says less than. Less than means the left side. So let's go ahead and shade it. All right, so right now we're going to find the probability that X is less than 156.25. So we're going to go ahead and find this probability. So in order to find this probability, we're going to do normal CDF. So for this one, what's my lower bound? Negative 10 to the 10 power. Even though it sounds ridiculous to say somebody could be negative infinity in pounds, you still put it because we don't really know where to cut it off. So you put negative infinity, you have to make it easy. What should I say is the upper bound? Yeah. So 156.25. All right. What should I say is my mean? All right, 182.9. What should I say is my standard deviation? All right, so 40.8. Cool. So for this one, if you notice, my standard deviation does not change. The reason it does not change because my sample size is still 1. If my sample size is bigger than 1, that's when the standard deviation would change to the standard error. But in this case, since our sample size is just 1, like it's still 40.8. So take a minute, enter that to the calculator, onto your calculator, and let me know what do you get. Good. All right, it looks like most of you got the same thing. So 0.2568. All right. So this is telling me like if we randomly select one person, well, not one person, but one male, the probability that they weigh 156.25 pounds or less is 25% chance. So there's 25% chance that this person weigh less than 156.25. So pretty much a quarter. All right, so let's go ahead and let's do C. So it says, assuming a worst case scenario in which the passengers are all male, what are the chances that the elevator is overloaded? Find the probability that that a sample of 16 male have a mean weight less than 156.25 pounds. So for this one, how many male did we randomly select? So you want to be careful because right here it says 16 male. So n is equal to 16. So for this one, we can't use the same standard deviation of 40.8. For this one, we do have to adjust the standard deviation. So we're going to have to find mu of x bar, but you're also going to have to find sigma of x bar. So for mu of x bar dt, because it's exactly the same thing, is 182.9. For sigma of x bar, you get 40.8. You divide it by square root of 16, and you're going to get, well, a bunch of you already got it, 10.2. So that's our new standard deviation. All right, so we want to do 156. 156 is actually over here. So let's say this is 156.25. So which side should I shade? Should I shade the left of the blue line or to the right of the blue line? There you go, left. So we shade all of this. Not that much. All right, everybody good on why we shade the left side? So you need to do it because you have a sample size bigger than 1. So if you look at it, it says we have 16 male versus in part B, it said we only have 1 male. So that's why you have to adjust the standard deviation or the sigma, because essentially we went from having just 1 male, or we went from randomly selecting 1 male to now randomly selecting 16 male. All right, so let's do normal distribution. No, normal CDF, sorry. So for this one, my lower bound, my upper bound, that is not going to change because that didn't change in this problem. What did change is the mu of x bar and the sigma of x bar, but mu of x bar is equal to mu, so we still get 182.9. But for this one, you have to adjust the standard deviation to 10.2. So now when we find this probability, we're going to find the probability that x bar is less than 156.25. So kind of notice the difference between this one and this one. So that way in a test or in a quiz, you don't mix them up. Like if you said probably x is less than 156.25, I'm telling you it's a sample size of 1. If I tell you probably that x bar is less than 156.25, that's when you know you have a sample size. All right, so if I enter all of this into our calculator, what do I get? So you get 0.0045. Yeah. And that's it for C. Any question in regard to C? All right, let's do D. So for D, it says which probability is greater, part B or part C? So we're using less than, if you look right here, this is less than 156.25 pounds. Oh, sorry. Yeah. I think I changed down the notes. Yeah, on the note, is it say greater than? So I should you should do the right side, but for this one, change to less than. So in the notes, just change it from greater than to less than for both B and C. All right. So which of the two probably is greater? The one for part B or the one for part C? Yeah, so if you look at it, you have a higher chance of selecting one male whose weight is less than 156.25 versus if you get 16 male, like the chances that the average weight of those 16 male is smaller than 156.25 pounds is not very likely. So if you look at this case scenario, so in this case scenario, like if you see an elevator with 16 male, you probably don't want to go into the elevator because most likely that elevator will be overloaded. Because the chances that the elevator is not overloaded is 0.0045. So the chances that the elevator is overloaded is something like 99.4 or 0.55%. All right, but that's it for that last problem. Any question for that last problem? All right, so let's do this next problem. Part B. All right, so for this one said the length of a human pregnancy is right skew distributed with an average pregnancy length of 266 days and a standard deviation of 16 days. For this problem, do we need to apply the central limiter? So it'll be yes, since the distribution is right skew. So we'll put yes since the distribution is right skew. So for this one said, what is the probability a randomly selected pregnancy lasts more than 260 days? So for this one, how many pregnancy are we selecting? So n is equal to 1. So if my parent distribution is equal to, well, is right skew, and if my sample size is equal to 1, like, does it pass the central limiter? No, because if you look at the central limiter said n has to be greater than or equal to 30. If you look at this, 1 is not greater than 30. So for this one, we say we cannot find the probability All right, so for this one, we'll say we cannot find the probability since the distribution is right skew and the sample size is less than 30. All right, and that's it for B. So for this one, we cannot find the probability because the data set is right skew and because the sample size is 1. So let's do C. So it says, suppose a random sample of 49 pregnancy is obtained. Describe the sampling distribution of the sample mean length of human pregnancy. So if I have 49 pregnancy, what's my sample size? 49. What's my mu in this problem? Like, what did it tell me the mean days for pregnancy was? 12, 6, so 266, correct. Yeah, 266. Okay, if you look right here, it says average 266. So we say average is 266. What about my standard deviation? What's my standard deviation for this one? Oh, 16. All right. So if you look at it, we want to describe the sampling distribution. So we want to say what mu of x bar is. Mu of x bar is actually equal to 266. What about sigma of x bar? Sigma of x bar will equal to sigma, which is 16 divided by square root of 49. So let's do 16 divided by square root of 49. So you say 2.29. All right. So for this one, can I say the problem is normal? Well, can I say the distribution is normal? So the problem tell me is normal? Yeah, so for this one, what you want to say it's approximately normal because you have to use the central limit there. Because you have to use the fact that n is greater than or equal to 30. So since our n, which is 49, is greater than or equal to 30, we could say that this is approximately normal. So you've got to be careful with that. Because if you apply the central limit theorem and the condition does pass, then what you have to say is approximately normal, not normally distributed. You only say it's normally distributed if the parent distribution is normal. All right. Everybody good on C. So for C, we say mu of x bar is 266, sigma of x bar is 16 divided by square root of 49, and we say that it is approximately normal. So let's do D. So for D, it says, what is the probability that a random sample of 49 pregnancy has a mean pregnancy period last more than 270 days? So here you go, 270 days. So for this one, is it possible to find this probability or is it not possible like for part, which part was it? Like part B. Like, can I find this probability or can I not find this probability? Yeah, so for this one, it is possible because our sample size is bigger than 1, because our sample size is actually 49. So that way for this one, we can actually find the probability for this one. So since we want the pregnancy to last more than 270 days, which side should I shade? Should I shade the left side or should I shade the right side? Oh, right. All right, so let's go ahead and do normal CDF. So we're gonna find the probability that the mean of those 49 pregnancies lasts more than 270 days. Cool. All right, so for this one, if you look at my lower bound, sorry about that. So if you look at my lower bound will be 270 days. If you look at my upper bound will be 10 to the 10 power. If you look at my mu was 266 days. So the cool thing about the TI-84, if you want to get more precise of an answer, what you can actually do, you can put 16 divided by square root of 49, and the TI-84 will actually do that for you. So I'm going to put 16 divided by square root of 49 for that way you can get a more precise answer. So let's go ahead and go to the TI-84. So turn it on, go to stats, oops, not stats, go to second, go to vars, go to normal CDF. So for this one, the lower bound is 270. The upper bound is 10 to the 10 power. 10 power. My mu was 266. My sigma in this case will be 16 divided by square root of 49, which square root of 49, you could put 7, because that's the square root of 49 is. So go right here, go to paste, go to enter. All right, so your final answer will be 0.0401. And that's it for your final answer. Any question in regard to the answer for part D? So let me transfer back to the notes. All right, so that's your final answer. So the probability, if we have 49 pregnancy, the probability that all or that the average of those 49 pregnancy lasts more than 270 days, well, there's only a 4% chance of that happening. So the probability that all 49 pregnancy, that the average of those 49 pregnancy lasts more than 270 days, there's only a 4% chance of that occur. All right, and that's it for that one. Any question in regard to this last one? Okay, so right now we were dealing with the mean and standard deviation. For the next chapter, we're gonna be dealing with proportion. So this is where it gets fun because essentially what you're gonna be doing, you're gonna be finding the mean, you're gonna be finding the probability of a proportion occurring, which some students find hard to do. So first thing, let's get some basic formula. We have p hat. So the way that you find p hat is x divided by n. X is pretty much how many objects have a certain characteristic. N is your entire sample size. So kind of imagine if I want to find the proportion of female in this classroom, X will represent how many female do we have in the classroom, N will represent how many total people we have in the classroom. So if we have, I don't know, 15 females out of, let's do easy math, 30 students, so P hat will equal to 0.50. So that's how you find P hat. P hat is X, which is how many people or how many objects have that characteristic. And you divide it by N, which just represent how many total samples do you have in your data set. Right. Any question in regard to P hat? All right. All right. So if you remember for the last chapter, we had mu of X bar, and we also have sigma of X bar. So for this chapter, we're gonna have something like that also. So you're gonna have something called mu of p hat, and you're gonna have sigma of p hat. So mu of p hat is equal just to p. P is the population proportion. P hat is the sample proportion. So just remember, p hat is the sample proportion. P is the population proportion. And if you look right here, here go our standard error. So our standard error is equal to square root of p times 1 minus p divided by n. So for mu of p hat is equal to p. Sigma of p hat is equal to square root of p times 1 minus p divided by n. Any question in regard to mu of p hat or sigma of p hat? Okay. So up next, we're going to go into the central limit theorem. So for this section, we also have the central limit theorem, but for this one, the condition is going to be slightly different. For this one, we're going to have two conditions. So for this one, we have to check to see if we have a large sample size. In order to check to see if I have a large sample size, what we're going to do, we're going to get n times p times 1 minus p, and that has to be greater than or equal to 10. If that's not greater than or equal to 10, then we say the large sample, we don't have a large sample. Any question on large sample? All right, so the next one is big population. So the thing is, we want to make sure that the population that we're sampling from is a big population. So the way that we check to see if we have a big population, what you're going to do, you're going to say 20 multiplied by your sample size and your population. And if you remember, the notation for population is capital N, should be bigger than your sample size multiplied by 20. Because if your population is actually smaller than sample size multiplied by 20, then you have to say that you don't have a big population. And the whole reason why you want a big population, because you want to make sure that the population is not like small, like only have 20 people or 30 people. You want to make sure that the population has like 10,000 people or a million people or something like that. Any question for big population and large sample? And like once we actually do it, it should kind of make sense to you. All right, so let's scroll on down. All right. So we're gonna get into how to find the probability for a proportion. So the first thing what you wanna do is first find the standard error. So to find the standard error, you do this. So then what you wanna do, you wanna find the z-score. So to find the z-score, you're gonna do this formula. So if you look at it, it's p hat minus p, and then you divide it by standard error. So the next thing what you want to do, you want to draw the standard normal distribution with the z value and shade the appropriate side. And then step number 4, you just want to use the normal CDF, find the lower bound, the upper bound, and then you do on your TI 83 or 84 calculator. Any question in regard to the steps on how to find the probability? So if you kind of notice, it's kind of the same thing as what we did before. The only thing different is you first have to find sigma of p hat versus in the last one you had to find sigma of x bar. All right, so let's do a practice one, and then that'll be it for today. So for this one, it says a simple random sample of a size of n is equal to 200 and whose population proportion with a specific characteristic is p is equal to 0.75. So if you look at it, I got n is equal to 200. I got p is equal to 0.75. So the first thing what I want to do, I want to describe the sampling distribution of p hat. So to describe the sampling distribution of p hat, we had to find mu of p hat, and we had to find sigma of p hat. So remember, mu of p hat is equal to p. So in this case, what would p equal to? Yeah, 0.75. If I want to find what sigma of p hat is equal to, I do square root of p times 1 minus p divided by n. So we do square root of 0.75 times 1 minus 0.75. And you want to divide this by n. N in this case is 200. All right, so let me go and do this on the TI-84. So in the TI-84, you go here. Let me do annotation. So you want to go, nope, so you want to go here second, and you want to go x squared. So you get the radical. So you go 0.75, and then you do parenthesis 1 minus 0.75, close parenthesis, and then divide it by 200. Press enter. So you get standard error 0.0306. So your standard error, usually if you get 4 decimal places, that should be pretty accurate. Right. Any question I got 0.0306 for my standard error? All right, so up next, what we're gonna do, we're gonna say, is this normally distributed? Or we're gonna say, can we say, is it normal? Is it approximately normal? Or is it non-normal? So, yeah, so standard is sigma here. But if you remember for the last one, we also call that normal. Well, sorry, we also call that standard error. Right. So for this one, what we want to do, we want to see if it's normal, approximately normal, or non-normal. So for this one, for the central limit there, we can check both requirements because for one of them, we have to know the population. So for this one, if you look at it, they don't really tell me what the population is. So for this case scenario, we're just gonna ignore that one. And what we're gonna do, we're gonna check this one to say, which one is it? N times P times 1 minus P, and that should be greater than or equal to 10. So for this one, we're gonna do N, which is 200. We're gonna do P, which is 0.75. We're gonna do 1 minus 0.75. And we're gonna see if this is greater than or equal to 10. And let me move this because all right, so I'm gonna do 200 times 0.75 times 1 minus 0.75. So the reason why they have greater than 10, because you want to have more than 10 success and 10 failure. So that's why they put greater than or equal to 10, because you want to make sure that you have greater than 10 success and also greater than 10 failure. Right. So if I do 200 times 0.75 times 1 minus 0.75, let me go to my TI-84. All right, so for this one, we're going to say 200 times 0.75 times. So for this one, if you look at it, if you do 1 minus 0.75, you get 0.25. So I'm not going to put 1 minus 0.75 because I don't want to do that extra work. So we'll do that. And you get 37.5. So if you look at 37.5, 37.5 is indeed greater than 10. So since 37.5 is bigger than 10, we're going to say that this is approximately normal. And that's it for that one. Any question on how we describe the sampling distribution? Cool. All right, so for this one, we're actually gonna stop here because I kind of want to show you two different ways how to do the probability. So I don't think I'll have enough time to show you both ways. So I'll probably do both of them tomorrow. All right, so that's pretty much it for today's lecture. Please remember for tomorrow, you are gonna have a quiz. So let me show you where the quiz is located at. And it's essentially, you're gonna cover what we went over today. So if today was easy, well, the quiz for tomorrow should be easy then. So what you wanna go ahead and do, just go over here. So you wanna go over here where it says week 5. And if you look right here, it's quiz number 7. Cool. All right, so quiz number 7, you're gonna have 25 minutes. There's gonna be 7 questions. So the chapter you're gonna cover is pretty much what we did today, chapter A. So the little part that we did for chapter 7 is not gonna be on this quiz. And you're gonna be what we went over on chapter 8. So you kind of review your notes on chapter 8 that you did today, so that way you could kind of know what should be on the quiz tomorrow. Any questions about the quiz or any question in general? Test two should be open. Let's see. Blah, blah, blah. Yeah. So if you go to test two, yeah, it should be open because it says after July 14th, you should be. No, this will be on the quiz. Remember, the quiz is all we covering what we went over on Monday. So this information that we went over today, that's what the quiz will be on Monday. Oh, sorry, on Thursday. Let's see. Yeah, I'll post it up right now as soon as I close out this meeting. The formula to check for the sampling is n times p times 1 minus p, and that has to be greater than or equal to 10. All right. Any other questions? All right. So good night. I'll post up everything. Everything should be posted before midnight. Well, the notes should be posted like in 5-10 minutes. The lecture won't be posted until like 12 or before 12. All right, guys. I'll see you tomorrow.